to discuss anomalous behavior of first element of each group, or you can say anomalous behavior of second period elements. Alright, so what happens, the second period elements show different properties in comparison to the other elements of their respective groups. So here you can see this is the second period. So these elements, this lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon, these show different properties as compared to their other member of the respective group. For example, in the S block element, this is S block. So in the S block element, the lithium and beryllium, these two elements have in the compounds have predominantly covalent character, while other elements of these two groups, when form compounds, they show ionic character, while lithium and beryllium show covalent character. Similarly, if you see the reactivity properties of these two elements, these are lesser reactive as compared to the other elements. We know that sodium and potassium show vigorous reaction with water, but that is not the case with lithium. It reacts slowly. Similarly, the reactivity of beryllium is less as compared to the other elements. And one more thing is there is a diagonal relationship between these elements. Lithium show similar properties as that of the magnesium, beryllium show as that of the aluminium. This is called diagonal relationship. No other elements, like elements from the third period or fourth or fifth, they do not show a diagonal relationship with other elements, but these second period show diagonal relationship. Now why is that? So we have earlier discussed the trend in atomic radii, electronegativity and other properties. So if you see, when we move from left to right, the size decreases, and when we move from top to bottom along a group, the size increases. But when we move diagonally, both of these effects get cancelled and nothing changes. Everything remains same. So that's why they show similarity in properties. Now, if you see in the P block elements, these elements have some very unique properties. First is they show p-pi bonding. In the second period P block elements, the valence in the valence shell they have 2s and 2p. So in total they have 4 orbital participating in bonding. So the maximum covalency shown by these elements is 4. First property is they show p-pi bonding. Second is the covalency is maximum 4. Third is they form hydrogen bonding. Alright. These three properties are because of these three reasons. These elements have smaller size as compared to the remaining elements of the group, higher electronegativity and non-availability of d orbitals. These elements do not have d orbital. If you consider the example of third period, in the third period you have 3s, 3p, 3d. So in total you have 9 orbitals. 9 orbitals that can take part in bonding. Alright. So if you see the example of covalency 4, let's take BF4 negative. Alright. And we have taken boron, let's take an example of aluminium. Aluminium can show maximum covalency 6 covalency. So these are the 3 reasons why these elements show this anomalous behavior: smaller size, higher electronegativity, non-availability of d orbitals. Now the lower elements, they do not form p-pi bonding, they form p-pi d-pi bondings, and the reason is, as you move down the group, the size of the p orbital increases and they have very diffused electron cloud. That's why the overlapping, sideways overlapping of p orbital is not possible. Hence, they form p-pi d-pi bonding instead of p-pi p-pi bonding. Now, this p-pi p-pi bonding has given an amazing property to the carbon atom. Carbon atom shows the property of catenation. That is due to the formation of carbon-carbon double bond, carbon-carbon triple bond. This is due to the property of catenation. Alright. So this is all for the anomalous behavior of second period elements.